Let's grab it. Now, this was, somebody noticed this one last time, the actual test we need to run. I think it was you, Veronica. You noticed a 2-sample t-test? It might have been Emily, I don't remember. Somebody over on this side noticed a 2-sample t-test before. Go find that one in your stat tests. It's right there near the top, 2-sample t-test. You actually do have 2 independent samples now. And that's why it's called 2-sample t-test, because you actually do have 2 independent samples. Yeah. You actually do have 2 independent samples. Yes. It asks you if you have data or if you have statistics. We have data. It's still in your lists, remember? It's still in your lists. So now you have to make sure that the TI is looking at the right stuff. We have data. List 1, make sure you match your numbers up to your hypotheses. List 1 is going to go with mu1, which is the cantilevers. So I'm happy with that. That list is list 1. Its frequency, we're going to call the number 1 because it's raw data. This is a throwback to 243. When you have frequencies and you have data, sometimes you've got both. In this case, it's raw data, so the frequency is just 1. List 2, actually mine's set up pretty well. List 2 is your V-break data, L2. Its frequency is 1, because again, it's raw data. Again, it's raw data. Is fair? Ish. Get there. All right. All you got to do now is pick the right sign. Pick the right sign. We got does not equals, we got less than, and we got greater than. It's definitely greater than, that's why I had you write this down, so you know what to pick. Eh? So you know what to pick. And again, you might notice this is the first time we've never had to put a mu naught or a p naught number in. Remember how we always had to put that in before? 0, 100, 0.75, 0.8, 12, whatever it was. We don't have any number because it's assumed the number is 0 because the average difference is being compared to no difference. Yeah. So the TI knows that. Fair enough? There's one. Good. Thank you, Danielle. Is looking at the next line now, which says pooled. Quick answer. Always leave it on no. Quick answer. That's a very, very good question. Pulling, from what I understand, pulling comes from when technology wasn't as prevalent, and there were assumptions made about. Remember that horrendous vomit-inducing denominator we just came together with? That was a lot for you guys to process at 8:15 in the morning. I'm not gonna lie. Back in the day, before technology, people had even less tolerance for it, I think, because you then had to go and calculate that terrible, terrible value. So pulling, from what I understand historically, pulling made an assumption and said, let's just assume the 2 variances are the same value. Now, our standard deviations are not the same value, and the variances are 4 times different, 1 to 4 if you square them. So I don't particularly like the idea of pulling, making assumptions about variances that I shouldn't. So that's why I say, just leave it on no all the time. I've never seen a good reason as to why you should pull variances. Any statisticians watching this can maybe think of an outlier case where you can, but on average, it's better not to. Cool? All right. Scroll on down, calculator draw. Calculator draw. Draw! I think so too. I'm going to check one thing. Yeah, I got all kinds of crap turned on. Let me turn that off. All right, here we go. I think we're ready. Here she comes. Here comes the t-distribution. We're looking on the right side, yes? We're looking on the right side for area. Here it comes, here it comes, here it comes. Where is it? Way! How? Define way! Oh! Come over here to our little hand-drawn null curve, which I love. Actually, let's do this. Let's do that. Go. Okay, so there's our curve, yes? P is not really 0, although it rounds to 0. 1, 2, 3, 4, 5, 6, 7. When do I stop? 12. 8. 9, 10, 11. It's out in the hallway, friends. It's out in the hallway at this point. It's out in the hallway. Can we believe there's another curve out there? I think we kind of have to, yes? I think we have to believe there's another curve. Yes? Because this is 12.6 standard deviations away. That's your test statistic, 12.6. It's very hard for me to believe, exceptionally hard for me to believe, that result belongs on this curve. It's very hard for me to believe that. I mean, that's like walking into a room, seeing 30 dudes that have an average height of 16 feet and going, you know what? Somebody told me once that the average dude height is 5'11", and even though I'm seeing this bunch of guys that have an average height of 16 feet, I still believe it's 5'11". That's silly. That's silly. When you observe data that's that different, on average, you have to believe that something has changed. Unless I have some kind of goofy deviant data, which I don't think I did. I tried to control for that, yes? So we got a test statistic, 12.6 standard deviations. Off the charts different, yes? Off the charts different. P-value comes back, it's calling it 0. It's not really 0, but it's basically 0. What's our conclusion? What would you tell your neighbors? Whoa, what did I tell my neighbor who saw me riding down his driveway? I can explain that. What did I tell him I was doing? I was testing my brakes, and what can I report to him?
It appears that B brakes do stop in this distance.
Boom! And it's statistically significant. That's the idea. You don't have to write that in. It's assumed that that's there. But now you have it quantified, backed up inferentially. Some of you say, I don't care about that. That's okay. You don't have to care about it. You're sitting in 244 to learn about it. So I apologize if you don't care about it. But now you quantifiably applied it to the sampling distribution, which means you get claim of population. Yes, wait, Danielle's got a question.
Oh, no, I was just saying.
Just making the connection, right? Hey, good! It's type 1 error possibility, right? We could be wrong with a type 1, but my God, it's 12.6 standard deviations away. Now, you guys did, Veronica, you did claim, of course, that going into this, you thought a type 1 error was the worst case scenario, right? Okay, and that's totally fine. But even if you lowered confidence on this test, right, or excuse me, even if you raised confidence to head off a type 1, you'd have to raise it ridiculously far in order to get that far out, wouldn't you?
Yeah.
So I think we're golden all across the board. And I've been riding home safely without laying my bike down since. Yay. Now some of that might just be the fault. Maybe I got a false positive. Maybe I did. Maybe I'm riding more carefully. That's hard to argue against, isn't it? But I like to think it's because I have better control on my bike at high speeds. Yeah. So anyway, in my life. Make sense? Good. So what you've just seen, we're going to do one more before I kick you out of here today. What you've just seen is, you've seen a way to independently test two means simultaneously. You're testing them independently, but simultaneously. And that's the point. You only want one template for these. You don't want to have two templates. If you have two templates, you lower confidence. You lower confidence, you increase the chance of a type 1 error. You don't want to do that. You don't want to do that. Questions you have for me? Make sense procedurally? Good. Grab your data sheets. Let's look at one more. Make sure you go home with a good working understanding of this. Another data set near and dear to my heart. ADHD and brain volume. I couldn't resist this one.